So, we'll present you the introduction of a semi-topological approach for mean-field models in the scope of dynamic and metadynamic recrystallization. I credit the work to Guillaume Smag, whose thesis was the origin of this talk. Yeah. Okay. So I will try to speak louder. So first, a small introduction about the industrial context to have an idea of the motivation of this work. It deals with open die forging of large components in austenitic steels. You have some pictures to have an idea of the size. And in the process, you have sequences of numerous heating, cooling, holding, and also a lot of passes of deformation. So you have a sequence of DDRX evolution and also metadynamic evolutions. Here you have a typical single peak curve, stress rate curve in a case of DDRX material with a transient domain with this peak, and after large strain, a steady state in which all the material parameters are constant in a dynamic equilibrium. So the flow stress, the average grain size, and even the grain size distribution are constant. And the steady state does not depend on the initial state. It depends only on temperature and strain rate, if these parameters are kept constant during the test. So for the question of industriality, it's essential to master the grain size to avoid too coarse grains in order to be able to make non-destructive inspection. So here it's not a question of optimization of the properties, in-use properties of the material. So in the case of metadynamic recrystallization during a holding time just after straining, you have first a regime of metadynamic recrystallization in which the main driving force is the difference in stored energy, and the kinetics is quite rapid. You have a log scale here. And after a regime of grain growth in which the main driving force is the surface energy of grain boundaries. And the kinetics is more sluggish in this case. Sorry. So the general modeling frameworks of recrystallization is with three kind of models: empirical fits, I think you know all these things; mean fields, in which we consider a grain embedded in an homogeneous matrix. It's quite simple, physically based, but will give you some issues with distributed properties like grain sizes. And it's possible to make full field simulation, but it could be very intense computing for heterogeneous processes in the industrial context I've mentioned just before. So we have tried to develop a semi-topological model, and the main idea is to combine some topology features with the affordability of mean fields model without a complete tracking of the detailed topology of the microstructure. So I'm coming back to the paradigmatic canvas of mean field models for DDRX. The first thing, it's not due to the recrystallization, it's just a question of the local description of the boundary condition. So in fact, we need the strain rate in each grain. In my case, we use a simple Taylor assumption. It means that the strain rate is homogeneous, but it's possible to use whatever you want here, for example, an ISO power assumption or a complex model if you want. For dynamic recrystallization, we need 3 equations for 3 main phenomena. The first, the second point in the model is the local constitutive equation. So it needs to model, we need to model the balance between strain hardening and dynamic recovery in the absence of recrystallization. It's quite easy to fit it to stress strain curves before recrystallization. We need a grain boundary migration law in order to model the motion of grain boundaries in such a scheme in which the grain of interest is embedded in the equivalent homogeneous matrix. We need also a nucleation law for the occurrence of new grains. We have to predict the rate of this occurrence. And the last point, not directly related to recrystallization, is to have some rules for the transition scale to come back to the macro scale, in which we have the definition of the equivalent homogeneous matrix to define what is the average dislocation density, and also it is a way to obtain predictors for the flow stress, the average grain size, and so on. So all mean field models for DDRX are using this canvas. To go in more details about the local constitutive equation, in fact it's possible to use what you want. The most common way is to use a one internal variable constitutive model, and this internal variable is the dislocation density, which is considered as homogeneous inside each grain. It's not true, but at the mesoscale we need to do such assumption. It is fitted to stress strain experimental curves before the onset of recrystallization, so it's not so difficult to do that. It's possible to use Cox making equation, Lasraoui-Jonas equation for the most popular. It's also possible to use a Power law, which is very convenient in this case because it's possible to integrate in closed form all the model. And this Power law equation here corresponds to a sweet model at the macroscale, for if you consider the macroscopic flow stress. We need also the same for static recovery when we are dealing about with holding time at a given temperature. So we use a simple kinetics of order 1. We need also a grain boundary migration law. So it comes from the thermodynamics of irreversible processes. More precisely, when it is linearized for small driving force, and in this case, the migration velocity is considered as the product of a mobility, material properties, times the driving force. And this driving force could be related to the stored energy for recrystallization, so the difference in dislocation densities between two grains, or between one grain embedded into the equivalent homogeneous matrix. There is also another driving force which is due to Laplace pressure or tension, surface tension, or the energy of grain boundaries. In fact, it is the same. But as grains are modeled by spheres in this kind of model, the interfaces are not shared interfaces like standard grain boundary in a real polycrystal. So the interface area is artificially doubled in this kind of model. So in fact, one has to divide by 2 the Laplace pressure in order to evaluate correctly the things. So if we write that in this case, the diameter rate is the product of 2m here you have the driving force due to the difference in terms of dislocation density. On here you have the difference between the grain and the equivalent matrix in terms of capillarity or surface tension. So we need also a nucleation law. Nucleation, it involves complex phenomena, bulging of subgrain rotations. You have some mechanism of necklace recrystallization, especially in the transient regime. You can also have repeated twinning as a mechanism for nucleation. So it's difficult to have a very precise law for nucleation. So we use classically a simple assumption like that, in which the nucleation rate is proportional to the average dislocation density to a certain power p, and commonly we use 3 for certain reasons. And also the nucleation rate is considered as proportional to the total area of grain boundaries in the system. So the sum of d square. And the last point to come back to the macroscale is the transition rule to macroscale. So it's necessary to have a kind of self-consistence in the definition of the equivalent homogeneous matrix in order to guarantee the volume conservation of the whole system. If we write that in the migration equation, it's possible with the migration equation to compute the volume change rate, and we know that it is 0, so it's possible to define the average dislocation density we have to take into account in the model to maintain constant the volume. And it is simply the average of rho weighted by the area of interaction between grains. So here it is the square of d because we have spheres. By the same way, it's possible to define the average grain size we need to use in the capillarity term for the migration in the migration equation. And in this case, we have to make averages of 1 over d weighted by always the d2. So we have the classical critical diameter in the Elot model. If you want to come back to these historical developments, so it's not new. And for the estimation of the macroscopic flow stress, as we have done the Taylor hypothesis, it is simply a volume fraction weighted average on the local flow stress is assumed to be proportional to the square root of rho. So the flow stress is obtained directly from the average of the square root of rho weighted by the d to the power 3. With all these 5 points, it's possible to use some model to predict what you want, the flow stress, the grain size, and during steady state, which is quite interesting because it is all the parameters are constant, even the grain size distribution. We can use the ergodic assumption, so it's possible to estimate the grain size distribution from the history of one grain. And if you use the migration equation, a grain is growing up to rho equals rho bar, and after it is decreasing. And you have a maximum. And it's in some cases the distribution of size is given by this. It is a closed form equation. in more general case, you have just an equivalent like that near the Dmax. But at least in this domain, you have always something like that in every cases. And this behavior is intrinsically a result of this distribution results from the deterministic character of the migration law used. So if you don't want that, you have to change the migration equation. And you know, experimental grain size distribution are not like that. So it is a reason why we have tried to, to develop a semi-topological approach. So the idea is to keep the simplicity and the relevance of mean field models. Do not follow the detailed topology of the microstructure as in full field models because it's too time consuming in our case. And to put some stochastics into the grain boundary migration equation. In order to test this idea, we have done a first trial using a random spread of the grain boundary mobility, just to see. And we obtain a better grain size distribution, but it is not enough, in fact. Or we have to have a very large spread to obtain grain size distribution similar to experimental results. So we have tried another thing, and it is the replacement of the equivalent homogeneous matrix in the migration equation using one neighbor. So we replaced the migration equation by this, on using a neighbor J, which is randomly selected. The connectivity selection is done with no consideration of reciprocity, so it is not a topology, it's a semi-topology. The neighboring relationship is fixed up the disappearance of one of both grains, but it's important to keep it. And for the volume conservation, there is just a compensation over the grain J when the grain I is changing. So it's quite simple because we have the volume changed by this. In this way, we have a double count of migration in the average, as we consider a grain as a grain I or a grain J, so we have to divide by 2, so we don't have 2 here. Here is a validation case concerning 304 still. We have equivalent stresses on average grain sizes with standard mean field model. But for the grain size distribution, here you have with standard mean field. In red, the experimental, and in blue, what we obtained with the semitopological thing, so it's much better. For the metadynamic recrystallization during a holding time, here you have the experimental average grain size on the two kinetics coming from the standard model on the semitopological model, so both are quite correct. And here you have a comparison with the semitopological grain size prediction on the experimental one after 300 seconds. So it's not perfect, but it's not so bad. And we have tried to make a comparison in the simple pure grain loss cases with several models, or a few models, available models. So in red you have as reference cases a computation made by Simlim or Digimut is more or less the same in fact. Here in blue you have our prediction with the semitopological model. you can compare with the standard mean field model, which is much lower. And here you have the Berk-Turnbull estimation. All these computations are made using exactly the same M and the same gamma, so there is no adequate parameter here. So it's possible to directly compare the results. And the conclusion is that we have a strong correlation between growing and shrinking neighbors in the microstructure, which is quite normal. Yeah. So just to conclude, I've shown some limitation of mean field models, especially for the distribution of grain size. I've described the introduction of the semi-topological model. We obtained some realistic grain size distribution, at least in context. And it's possible to make a series connection for multipass processing. So it's a good way to model sequences of DDRX and MDRX stages, and it's a way to optimize microstructures in the industrial processes I've shown in the introduction. And you can have a look on this article. Thank you for your attention.